Okay, thank you very much, Dieter, for the introduction, and welcome everybody. My name is Martin Müther, and I'm responsible for the program and project management within the commercial powertrains at FEV. I would like to explain to you a little bit about the development process of large bore engines. And here on this slide, you can actually see how such a development process looks like. As most of you probably know, over the last decades or years, the development time of large bore engines has significantly decreased. Shorter the time to markets need to be achieved. And this is how the timeline could look like or does look like today. So 36 months for a new engine is really benchmark, but it really requires that there is a robust plan behind it. It requires a lot of front loading. It requires also single cylinder engine investigations, and it also requires virtual calibration. And I will guide you a little bit through this process, starting from the requirements over concept work, then into detailing and the single cylinder engine testing over to the end when the engine is available to the market according to our plan and according to what we do within 36 months. So let's have a look at the next slide. You can see that here, what I mentioned before is that in the beginning, it is absolutely important and mostly required to have a clear definition of where we want to go to, what is required. As always, when you start a project, the definition of the requirements actually determine how the project will go. And this is here now an example for a high-speed engine. And we start on the right side where you can see over the years the share of different applications of large bore engines, in this case, a high-speed engine. So what you can see is that there is a significant share of different applications, for example, railway, marine, construction, and so on. And the share of the different applications is so significant that it cannot really be ignored. And they have to be taken along in the development to really get an increasing volume of engines and also to reduce the cost of engines to make it a profit. So if you have a look at this, you can see on the left-hand side different applications, and we have listed here a little bit the different requirements or special requirements for different applications. I will not go into too much detail, but for example, the power-to-weight ratio, the life cycle costs, the reliability, and so on, are a little bit looking at the different applications of different importance, and this really needs to be elaborated clearly at the very beginning of the project so that it is clear what targets we want to achieve in the course of the 36 months. So what comes afterwards, after all the requirements are actually defined properly and written down and everything is considered, we need to go into the concept work. And what I have brought along here as an example is for a hydrogen combustion system is the proposed process, how to really get into a combustion system in the concept phase when no hardware is available at that time. So that means that everything has to be based on simulations in different ways. And what we have elaborated for different applications are actually validated tool chains. And I will very quickly guide you through this, how we do this. We start on the left-hand side with different input parameters that are connected to base geometrics of an engine. Then we make 0D simulations. We get into a heat release rates. After that, we do 1D simulations. We get into more information that are connected to intake and exhaust pressures and so on. We can start to define hardware, compression ratio, valve timings, and so on. After that, we combine the output in a 3D CFD simulation where we have information about the mixing of different fuels. And then we can define also the injector specifications and also where it is supposed to be located. And then at the very end, we get into further 3D CFD, first mixing, in the last step, the combustion. We're really also taking into account the reaction kinetics themselves. We know about knock control, knock events, about emissions and so on. And this is a purely these are purely simulation tasks, but what is very important is that they have to be properly validated. This means that all of them, when you start with this project, you need to have a solid base, meaning in earlier projects, there has to be an alignment or a validation with, for example, single cylinder engines, also multi-cylinder engines, but also combustion chamber investigations with different fuels that we really know how does a fuel spray look like when it is injected into specific boundary conditions. Yeah, a further example for the concept work is, for example, the lifetime prediction for a piston. And this is a process that we have developed, and you can see here the individual steps. And this is all simulation, like I mentioned before, and we use different programs and tools for that. So what you can see here in the concept phase, that we do make a piston layout. On the left-hand side, you can see the first step. We put the boundary conditions on a developed piston, like the heat transfer coefficient, the temperature of the gas, but also the oil cooling boundaries. Having that done, we know more about the real piston temperatures. Later on, we can calculate stresses and high cycle fatigue. We can go into bolt fatigue. We know about contact pressures and so on. And at the end, based on the simulation model, it is possible to predict the lifetime or the thermomechanical fatigue of a newly piston without having hardware, without having made any tests. So that is very important, because this is all part of the front loading, that once you get into hardware in modern development processes, you know that you are already at a rather ripe, at a rather mature state. Another example, also done in the concept phase, is here, for example, the vibration analysis. So, for example, this is a model here, a multi-body simulation, where we make a virtual validation of the vibration behavior of the drivetrain of the engine before a first prototype is built. And you can see some results here. So in this picture, you can see different measurement points. So actually, these are analysis points, because it's not a real measurement, it's all simulation. And then you can derive from the simulations actually different diagrams with different values. You can see that at the bottom. And for specific parts, for the specific components or materials, you know what the limits are. And you can compare these limits with actually the outcome of these simulations. And you can very quickly see how safe are you. Do you have a risk of failure? You can make a first analysis of the lifetime. And so we suggest to employ this very much to really get a good feeling about the engine before it is built in the very early concept phase. Yeah, another point, despite of the timing, is for sure always the weight reduction in modern engines. And what I want to show to you here is an example of weight reduction. And the next slide will explain a little bit about a possible process, how to select the firing order. So in this example here, we do have a marine application with a bore of 180 millimeters, a bank angle of this V16 engine of 60 degrees. Yeah, and we have actually analyzed how the firing order actually has an impact on the stress level, and corresponding to that, with a lower stress level, how the weight could possibly be reduced. So coming from this base engine, you can actually derive different crankshaft layouts. And in this case, it is possible to derive 6 different mirror symmetric crankshaft layouts. They are named here A to F, and all of them enable actually in engine external balancing. And these are the base for the further analysis. If you make the first step in the vibration analysis, you have a look at the mass elastic system and also at the Campbell diagram, and you can see that all of these actually have the same mass elastic system. So this means this diagram up until now looks the same. So I will not go into much more detail on the vibration here, but what I would like to do is to actually go into more details of the vibratory results that come on the next slide. So here, for the 6 different geometries of the crankshafts, you can see over the engine speed, the stress amplitude. And just very brief introduction, what we do is we simulate all different possible firing orders and see what is the impact on the stress amplitude. And for the further explanation, I will make a focus on 2 of these variants. These are the variants A and C. They have different crank orientations, and this means that they actually have a different internal balancing. And this also means that they can possibly make different firing orders. And for these V16 engines, like I said, there are actually 128 different firing orders that can be selected. And you can see the result of all of these 128 different firing orders in the gray area in these diagrams. And you can see that depending on the firing order, the stress amplitude can easily double or be very much lower. So there is obviously, and we know that, a significant impact on the stress amplitude, on the stress level by the actually firing order. Going one slide further, you can actually see here in more detail. I will keep it a little bit short. So for sure, you can see here the resonances on this slide, the 1.5, 2.5, 3.5. actually connected with the different eigenmodes. But what you can see again in more detail here now, that there is a wide range of stress amplitude depending on the firing order. And you can see here also, and that is very interesting, in black, the curve, these are firing orders suggested in literature that are usually used. And you can see in this black curve here that these suggested firing orders are not the best ones. So if we really make a detailed analysis by simulation of different firing orders, it is possible to find firing orders that are even more beneficial, that keep a bigger distance actually to the limit stress amplitude. And therefore, if that is being done, you can select more beneficial firing order. And if you combine this optimized firing order with the optimization of counterweights, then it is possible in this specific case here to reduce actually the weight of the crankshaft assembly by up to 20%. So this is also something what really gives a benefit in the weight reduction, purely simulation, and part of the concept phase of the project. Again, really making sure that when going into the hardware, and the crankshaft, if you order it for a large engine, is hugely expensive, that really when you do that, you know you have made the right and proper selections for the requirements that you would like to fulfill. So these are some examples in the concept phase. I explained that before, and for sure, these are only examples. So on this slide over here, I would like to give you an overview of further possible simulation applications in the concept phase that support the aim to make a purely virtual design release, and to avoid cost-intensive actually test operations with a lot of loops. This in a short development time frame cannot be allowed to make expensive loops where you have to procure hardware again and again. At the same time, and you can see that on the right-hand side in the bullet points, it also must be clear that today the material utilization is steadily increased. We want to achieve higher brake mean effective pressures. We increase the peak firing pressure. So this means that the gap between the actual usage of the material and really the limit of the material gets closer and closer. And this for sure needs really solid and robust simulation techniques, which are validated to really be on the safe side, but not too far away from what is required. It will increase otherwise the cost and also the weight of the engine. Part of this development plan, and I said before, the benchmark today is 36 months. It is, from our point of view, really important to go into combustion development also very early after the simulation phase, going very quickly into the single cylinder engine phase, because it gives you really the benefits to quickly, with limited, let's say, price efforts or cost effort, to really get a lot of knowledge about the engine development. And we use the single cylinder engine, and Max has mentioned that before, for two reasons. One is the combustion development with the target to reduce the raw emissions and also to optimize the fuel consumption. And we also use it for an initial mechanical development of the power unit. So initial durability testing just of the power unit can be done, and also some initial components that are part of the power unit can be validated also at a very early stage, being then the prerequisite before going really into the multi-cylinder engine build-up and having all of these parts that are one time used on the single cylinder engine 12 or 16 or 20 times, and really then going to very cost-intensive testing. On this slide here, and that was also part of the presentation before, coming from the more conventional development program with a time duration of over 42 months, this really gives us the benefit to very early go into the setup, really do a lot of testing initially, combine that also with virtual calibration. I will talk about that a little bit later, to really quickly then later on go into the multi-cylinder engine testing, but requiring only a shortened testing time. Ideally, from the single cylinder engine testing, the thermodynamics are all completed. You make a validation on the multi-cylinder engine test, and then you can go on with the functional testing and the durability testing, which should be the key for doing the multi-cylinder engine testing. Should not be, if you want to achieve really short development times, the combustion system development itself. Going on from here, another point to reduce the timing in the development is for sure the virtual calibration. And you can see that here on this slide. The general idea of virtual calibration is that there are specific models for different components or engines or even vehicles, and these so-called model plans are connected to real control functions of the control units. So this means you have the functions, you can later on calibrate these functions, and they interact with a model that reacts like the real engine does. And this is what you can see on this slide, and we apply this very much to shorten the development time and to get more knowledge in alternative calibrations and for different applications at a very early stage, while you cannot build up all of the hardware for different applications. Now, also here, what is the impact? How is actually virtual calibration part of the development process? Now, here you can see the very conventional development process. It starts with a concept study, then you make the hardware layout, you get into engine calibration while you're doing engine testing later on. And I mentioned that before, that today's engines are multi-purpose. It's not just one application. Then you go into application calibration, and after that, you go into the market. Now, if you apply the virtual calibration, and we call it virtual calibration platform at FEV, the system or the development plan looks a little bit different. So you start with a concept study, you go into the hardware layout. At the same time, you already start to build up the virtual calibration platform. And for building it up, you make use of a library, you make use of models that were used before, and you train them, you calibrate them. And then before even going on the test bench with the full engine, you can make a pre-calibration with this virtual calibration platform, so that the area where you are looking into when you make the more detailed calibration is much smaller, and you can then be a lot quicker. So you can see then the engine calibration and optimization will be a lot shorter, the effort will be reduced. And later on, when you used also these results from the test bench to continuously validate the virtual calibration platform, you can use this platform also to make a pre-calibration of different applications. And this also means that the actually testing of these applications on the test bench can be executed with less effort, meaning we're looking into a reduction of the time frame for the development, but also into a cost benefit. How does that look like? I mentioned before that for shortening the development time, it's important to do a lot of front loading to make use of the different tools that are possible, like the SCE, but also the virtual calibration. And on this slide, I would like to explain to you how that actually interacts. So if you start to develop on the left-hand side, in the bottom, you can see that if you start to develop by simulation the initial boundaries, later on you build up the SCE, and then on the single cylinder engine, we start with a global design of experiment. So we make a lot of tests in different configuration of parameters, different loads, different engine speeds, and so on. And from that, actually, by model training, a cylinder model is derived, which has a lot of information about how the combustion system, how the engine will behave. Combining that, or this is combined with further tests that come from specific component testing, for example, specific tests that give you the turbocharger map. Actually, this is combined into one model, and later on, you can see that on the lower right side, this is combined into the mean value simulation, which is the base for the virtual test solution. And like I explained before, if you do have the virtual test solution, the virtual calibration, the platform, you can use this to make pre-calibration before you go into the test bench. And you can use it also not only for pre-calibration, but also for validation. And then you go into testing. And for sure, what is always important, that the results from the real testing are used to then again revalidate the simulation model. And by doing this, the model will become better and better, and later on can be used also after the project for future projects, for derivatives, for different applications, for further developments. So this is something that will stay with the development for next steps, also when the initial project is actually finished. One more slide you can see over here. How does that look like? I explained that a little bit on some slides before. So you can see here that we do have at the very bottom different plant models that are available. We use it for previous projects where we know that they have a proper base, they can be used, and these are connected with the controller models that are coming from real applications, or that are part of the real hardware, the control units. And all of this together also with the power train control, where actually it is developed or described how the engine and the whole setup is supposed to be operated. So all of this is, let's say, implemented into one simulation environment, into Simulink. And in this environment, actually, this virtual calibration, the whole setup can be operated and can be, for example, be used for calibration. This whole system is possible to be operated in real time, so you can make changes of parameters and see what is the reaction. What also can be implemented are different hardware components. They can be directly integrated, and it is very easy to calibrate this model. And I will show a little detail of these models that are actually lying behind. It is very easy to calibrate all of this based on different data sources. They can come from the test bench, they can come from the vehicle, or from component testing. So based on these input parameters, the models and the whole setup can be trained, and to quickly achieve a maturity that is needed for virtual calibration. I want to show on this one slide here how, for example, the engine model looks like. Now it looks a lot more complicated than the slide before, where it was just blocks. So here, this is our model that we use for modeling the engine. It is very complicated. Our approach is that we always have a full model for a specific component, so that then we can strip it down, that we can simplify it to then use these parts of this model which are required for the specific project. And then actually different models are used for the single components inside of this overall model, and they are filled with data. And then at the end, it is trained, it is improved, so that this can be then used as a planned model in the virtual calibration that really reacts like the engine without operating the engine. So this slide sums a little bit the presentation up. I mentioned it before, for shortening the development time, for reducing the costs, for at the same time increasing the, for example, power or what we take out of the components, going closer to the limits. A really robust and reliable development program is absolute key for the introduction to the market, because in this time we really need to take down the risks, we need to avoid risks, and we need, like I said, we need to reduce these development costs. And I mentioned it before, we need at the very beginning a very detailed requirement analysis. It is absolutely key for a successful project. And like I mentioned before, every individual application has its very specific needs. So out of this, the requirements need to be derived. Success factors for achieving, or success factors are actually the reduced time to market, the reduced development costs, and it is absolutely not acceptable to really go into a lot of loops with different hardware variants. It is much too expensive, it is much too time consuming, so this needs to be avoided by the front loading, by simulation, by single cylinder engine. And this comes last. A robust and reliable development program is mandatory. We need these parts of the process that I explained, the simulation techniques, we need the single cylinder engine testing and the virtual calibration. Bringing this all together in the proper way really brings us to what we said before, the state-of-the-art development process, or the benchmark process of going down to 36 months from zero, from having a clean sheet to an engine that goes into the market. Okay, so this summarizes my presentation. I thank you very much for your kind patience and for joining this. And if you have any questions, we are ready to answer them now. So I hand it back to Dieter.